Okay, as we start our section on probability in chapter 4, there's a couple concepts that we want to make sure that we're clear on. Um, First of all, just how do we interpret probability? Probability is usually going to be expressed as a decimal, that is ranging between 0 and 1. Yeah, a lot of times we can communicate it also with as a fraction or as a percentage, and that's probably what we're used to. But in this class in statistics, we're going to communicate it most often as a decimal. So something written as 0.001 here, basically that's 1,000th, corresponds to an event that rarely occurs. Something identified as 0.99 or 999 thousandths corresponds to an event that is very likely to occur. So you need to be able to interpret the decimal notations. Now, just as we move forward, obviously we're going from one range to the other, from one end of the range to the other, from very rarely to very likely. We've got a whole lot in between here. We've got 0.5, where we would recognize that as 5/10 or half, corresponds to an event that is equally likely to occur as to not occur. Okay, so obviously we're moving from rarely to normal, equally likely, not likely, all the way to the other end of the spectrum where it's very likely to occur. So we're going to interpret all different kinds of events. Okay, an event is a collection of results or outcomes of a procedure. Um, we could go into single, compound events and so forth. We're not going to get into that a whole lot, but we do need to be able to think about the sample space. The sample space for a procedure consists of all possible simple events. Okay, with the example of a birth, one birth is one event. It has two different outcomes. Either it's a boy or a girl. And so we could communicate this in brackets like this, girl and boy. There's two outcomes for one event. If we were counting this, you can communicate this in exponential form. Whereas the number of outcomes is on the baseline, the number of events is up in the exponent. This makes a little more sense as we get moving along with more complicated sample spaces. With three births, the sample space consists of 8 different simple events, basically because there's 3 different events going on here, 3 births, 2 different outcomes for each birth. So we could put this in exponential form as saying 2 outcomes for each event, and there's 3 different events. So 2 to the third would be 2 times 2 times 2, which would give us 8. That would be a much easier way to calculate that versus trying to brainstorm the sample space. So I was brainstorming it here, but then I'm going off into the side here. It looks a little sloppy. I apologize for that. But I'm trying to help you think about the algebraic way that you might think that through. We could go on and continue talking about the fundamental counting principle here. That is part 1, what we've just talked about. Now, part 2 gets a little more, well, actually, I'll continue another example here with part 1. When making random guesses for an unknown 4-digit passcode, each digit could be 0, 1, all the way through 9. So we have 10 different outcomes for each digit. Each digit is considered its event, a single event. So we're going to have 4 different events here if this is a 4-digit passcode. First digit, second digit, third digit, fourth digit. Now the thing is I've put a line here saying this is the event, but on that line I wrote 10 because there's 10 different outcomes for each of those, the first event, the second event, the third event, and the fourth event. Now actually using the multiplication rule here, I would multiply these all together to come up with a total of 10 to the 4th power, or 10,000 different outcomes. Okay, actually I'm utilizing a combination of the multiplication rule along with this fundamental counting principle. But we can see that if I wanted to calculate what are the chances of just randomly guessing what I think this 4-digit passcode would be, well, the thing is there's 10,000 different passcodes. The chances I'm just going to randomly guess the correct one is 1 out of 10,000. And so we could write that as a fraction 1 over 10,000 or 0.001 or 1,000th in decimal form. We're going to think about this a lot in decimal form. But you can see when it comes to calculating probability, we have to know the sample space. How many different outcomes are in that sample space? So we need to think about the different ways that we count that sample space. And this fundamental counting principle is one of those ways. Another example of the fundamental counting principle, if one event can occur in m ways and a second event can occur in n ways, the number of ways the two events can occur in a sequence is m times n. Now that's kind of a mathy way of putting that, but a lot of times you have maybe encountered this in previous math classes where you were told, hey, you've got 2 pairs of jeans and you've got 3 different t-shirts. How many different outfits do you have? So I'm letting M1 be my pair of jeans, my first jean. M2 is my second pair of jeans. And 1, 2, and 3 are our t-shirts. Well, I could combine our first pair of jeans with the first t-shirt or the second t-shirt or the third t-shirt. And I'd have 3 outfits right there. Or I could combine the second pair of jeans with the first, second, or third t-shirt, and I would have 3 more outcomes for a total of 6 outcomes. Now, brainstorming that with this tree diagram, which is what we've done over here, is kind of painstaking. And if we had a whole lot more than just 2 and 3 different ways to do a single event, this would be really complicated. Or we could just multiply the 2 times the 3 to get 6 to recognize that there's 6 paths or 6 different outcomes. Okay, so counting principle is really important. Now we need to talk about the different types of probability. There's basically 4 different types: classical, empirical, subjective, and simulation. But we're going to be calculating with the classical and the empirical exclusively. We're not going to talk about the last 2. But classical probability is basically the probability in theory. Then you're looking at the number of ways something can occur divided by the total number of ways possible outcomes. And this is given that each outcome is equally likely. So classical probability, the number of ways divided by the total number of possible outcomes. Empirical is kind of retrospective observations. You're looking at the number of times something occurred divided by the number of times the procedure was repeated. So that is more of an observation looking at the past and analyzing things. So we're going to practice some of these. I've got an example here where we're identifying the sample space if we roll one fair six-sided die with one hand and flip a fair 2-sided coin with the other hand. I can create a chart here. Along one dimension, I'm going to list the different outcomes for the first event. Along the other dimension, I'm going to list the outcomes for the other event. Okay, so I'm going to be looking at some different combinations. Find the probability of getting 4 paired with heads. So I'm looking at a 4 along the outcome of a 4 along the dimension that we identified our dice. Paired with heads, we can see that can only happen one way out of a total of 12 different outcomes. We have 12 different cells here, so that's our total. So 1 out of 12 would convert to decimal form as 0.083. Again, fraction form or decimal form. Finding probability of getting an even paired with tails. 2, 4, and 6 are our even outcomes. Paired with the tails would be 3 different outcomes, so 3 out of 12, which would reduce to 1/4 if you're going to put it in fraction form and simplified form. And then you could write that as a decimal of 0.25. The probability of getting a blackjack doesn't even pertain to this scenario, so that would be 0. Okay, so that would be an example of classical theoretical probability, because we're calculating the number of times something could occur, the number of ways something could occur over the total possible outcomes. Okay, next example, texting and driving. In a study of U.S. high school drivers, it was found that 3,785 texted while driving during the previous 30 days, and 4,720 did not text while driving during that same time period. Based on these results, if a high school driver is randomly selected, that's a phrase that we're going to find a lot in this class, find the probability that he or she texted while driving during the previous 30 days. So we're looking at a part out of the total. So we need to figure out the total by adding the number that texted plus the number that did not text. So that's the first thing, is we need to come up with our total. That's what goes in our denominator. And then we're trying to calculate the percentage or the probability of selecting someone who did text was 3,785 divided by the 8505, and we get 0.445. So 44.5% of the high school drivers in the survey texted while driving in the previous 30 days. Basically, if we're going to randomly select one student, that means we've got a 44.5% probability of selecting a student who has texted in the previous 30 days. Now, this is an example of that retrospective or the empirical probability, because we're looking at a past observation and looking at the number of ways something occurred over the total number of times it occurred. Okay, another concept that we come across in this section is the whole concept of complements. So we're going to do another example here and talk about an event and then its complement. So skydiving. In a recent year, there were 3 million skydiving jumps, and 21 of them resulted in deaths. Find the probability of dying while skydiving. Okay, so this is 21. This is what was observed. 21 out of 3 million. And when we divide that out, it's a really small percentage of people who died while skydiving. When we put this in percent form, it's 0.007, basically 7/10,000ths of a percent chance of it dying while skydiving. If we want to think about the complement is denoted by this A prime. That little bar above there means A prime. Is all the outcomes where event A did not occur. So basically, the sum of these two should equal the entire sample space. This is a really important rule that we're going to use a lot going forward, because we're going to turn it and calculate a complement by taking a probability away from 1. So in this example, find the probability of not dying when making a skydiving jump. So I could take that 1 minus the probability of dying while skydiving to get our complement. So we have a much, much, much higher chance, almost a 100% chance of surviving a skydiving jump. Nonetheless, I probably won't be doing it any day soon, but this was a decent example on using complement. So this page, you got some example of calculating the different types of probability as well as the complement. Okay, the law of large numbers. As a procedure is repeated again and again and again, the relative frequency probability of an event tends to approach the actual probability. This basically means that the empirical, what actually occurs or is observed, approaches the classical or the theoretical probability. So a good example of this is if I had a class of, say, 12 students, and I gave every one of them a die, and I said, roll your die, we would expect that we could get somewhere close to, 2 people would roll a 1, 2 people would roll a 2, 3, and so forth. But it probably isn't going to come out exactly like that. There might be, 1 of one outcome and 3 of another outcome. It's not going to be 2, 2, 2, 2, 2. Not likely, anyway, because there's going to be that just inherent randomness. But if I brought in 12 die to my 12 students and said, okay, our only activity today is everybody's going to roll that die 1,000 times, and we're going to see how many we get. That would be a really large number of rolls. And we would expect it would come out to be pretty close to, about a sixth of the time you're going to get a 1, a sixth of the time you're going to get a 2. In other words, out of 12,000 rolls, you could figure pretty close to 2,000 of them are going to be a 1, a 2, a 3. So that's what we mean by the law of large numbers, that empirical observation tends to approach the theory of probability as we increase our numbers.